All right, in this lesson, we're going to use what we did in the previous lesson about finding area approximations, but now we're going to find the exact area using limits. So let's review what we have from the last lesson. If we draw a rectangle like this, that's called a left-hand rectangle. And if we draw a rectangle like this, that's called a right-hand rectangle because we're using the right endpoint to find the height. Here we're using the left endpoint to find the height. And we don't want to say that a right-hand rectangle is always above the line because it depends on the slope of the line. So here if we have a left-hand rectangle, left-hand rectangle is above the curve. A right-hand rectangle is below the curve. So that depends on the slope. And there are questions on the AP test about over approximation and under approximation, and you're going to know whether it's over or under based on the slope, if it's increasing or decreasing. Okay, so we'll divide this up, and we're gonna do 4 rectangles. So if we have the upper sum, we have to divide this into 4 subintervals. So there's 1/4, 1/8, 3/8. And if we're going to find the upper sum, we would need the right-hand rectangles. The lower sum uses left-hand rectangles. So the upper sum is going to be base times height, base times the height. The height is the y value of the function, and the function is radical x. And then we'll have base times the height here is at 1/4. Base times the height of this is at 3/8. And the height is at 1/2. So we have 0.2716 for the upper sum, and the lower sum is, here we have a base of 1/8 times a height of 0. So we don't have to write it, but just know that there's one rectangle that's an area of 0. Then we'll go base times the height is radical 1/8. Base times the height. The height of this rectangle occurs at 1/4. And the height of this rectangle is at 3/8. So that's going to be 0.1832. And we should put approximately. So we know that the actual area is between these two numbers. And I think that's enough review of that. Just because we have a lot to do. Now let's look at limits. Okay, so let's find the limit. This is the type of expression we're going to end up with when we're finding the area using a limit. So let's just start expanding that. And then we have to expand that. Here's a way to keep track of everything. 2n plus 1, n squared plus n. 2n times n squared. 2n times n. N squared times 1. N times 1. So now we have 2n cubed plus 3n squared plus n over 6. Then let's put the 6 out in front and put the n cubed under each of those. Reduce by 2, and we have 2 plus 3 over n plus 1 over n squared. Then as n goes to infinity, these go to 0, so we just have 64 over 3. Multiply by 2, we get 64 over 3. Let's try another one of those. Okay, pause the video and try that one. Just expand that. Put the 2 out in front. N squared can go under each of those. And that'll be a 1. 1 over n. As n goes to infinity, that goes to 0, so we just get 1/2 times 1. All right. So we can think about this graph, this function like this. We have x squared, it got shifted up 1, and it's a parabola. We're going from 0 to 3, and we want to find the limit as the number of rectangles goes to infinity. So let's just look at how big a rectangle is. If we have n rectangles, there's a little break in the graph, and then we'll go to the end. It doesn't matter if they're upper or lower sums. So if we have n rectangles, then we have 3 minus 0 divided by n is the width of a rectangle. The width is the total interval, 3 minus 0, divided by the number of rectangles. So that's 3 over n. Now let's think about it. Let's think about what each x value is going to be. So we can just use right-hand rectangles. It won't matter because we're going to have infinite rectangles. So there's 0, and then this x value is 0 plus 3 over n because the width of the rectangle is 3 over n. And then this x value is 0 plus 2 times 3 over n. And that x value is 0 plus 3 times 3 over n. And it's going to go all the way to 3. If we know all the x values, if we represent all the x values, then we can find all the y values, and then we can find area represented in terms of n. So now let's look at x values and y values. So we have x, y. We've already started looking at the x values. And that goes down, and we're going to call this 0 plus I 3 over n. That continues on to 0 plus n 3 over n. So what's happening is when I go n times 3 over n, that's 0 plus 3, and that is the end point that we need, and that means we have n rectangles. Then the y value at each x value is just going to be using the function x squared plus 1, and we're going to just have 0 plus 3 over n squared plus 1. 0 plus 2 times 3 over n squared plus 1. 0 plus 3 times 3 over n squared plus 1. 0 plus I 3 over n squared plus 1. All right. Now let's look at an expression for area. And before we continue, we need to review this. That the summation of from I equals 1 to n of a constant is c times the constant. If we go 1 to n of I, it's going to be n plus 1 over 2. If we go from 1 to n of I squared, we have n plus 1, 2n plus 1 over 6. And there's one for I cubed, but we don't need it for this problem, but we saw that in the previous lesson. Okay, now let's multiply each y value times the width. So that means we need a y value times the width of the rectangle. The width is 3 over n of each rectangle. So that means the area of the ith rectangle is going to be there's the height of the ith rectangle times the width of the rectangle. And this represents all rectangles because we have an I there, and then we're just going to have the sum from I equals 1 to n, and this is representing the area of all the rectangles. Let's simplify that, and then we want to find the limit as n goes to infinity, and then we'll have the sum of infinite rectangles. So we don't have to have the 0. Let's just simplify this. No 0. We're going to square that, and we're going to have I made a mistake here. We need to have that. So we're squaring the I also. So it's I squared and then 9 over n squared plus 1 times 3 over n. All right. And then we can distribute that, and we're going to have summation, and that's going to be 27 over n cubed okay, and 27 over n cubed times the summation of I squared. But we know the summation of I squared is just this. I'm going to copy this and then multiply it by 27 over n cubed. So we have n plus 1, 2n plus 1 over 6. 27 over n cubed. This, in terms of I, is just a constant. Since n is not changing, here's a constant, and we're going to have 3 over n. The sum from I equals 1 to n of this is just going to be n, and that's using this formula. If you're going to add up a constant n times, you have n times the constant. So here we have a constant. In terms of I, it's a constant, and we do this n times, so it's n times 3 over n, and so that's going to cancel. We get the plus 3. All right. So we've already seen how this expands. We did that in a previous problem, and it turns out to be 2n cubed plus 3n squared plus n over 6 times 27 over n cubed plus 3. So all of this is going up there. So in the previous two examples ago, we looked at this and we expanded it to get that. Now let's just put the n cubed under there. All right, so we have 2 plus 3 over n plus 1 over n squared. We're putting n cubed under each of those. Times 27 over 6 plus 3. Now, this represents the area of n rectangles. Let's find the area of infinite rectangles, and all we have to do is find the limit of this as n goes to infinity. So now we find the limit as n goes to infinity of that. And we have 0. As n goes to infinity, that's 0, 0. So we have 2 times 27 over 6 plus 3. And that's going to give us cancel that. 27 over 3 is 9. 9 plus 3 is 12. So we know that the area, the exact area under the graph is 12 because we've added up an infinite number of rectangles. And when there's an infinite number of rectangles, then there's going to be no error. The rectangles are infinitely narrow, so that means we're not going to see any error like this, where we get an over approximation, or here we could have an under approximation. Okay, find the area. So we're done with that. Find the area under the curve. Find the exact area using a limit. Pause the video and try that one. Shift it up 1, and it's a negative x squared. So we have that graph starting, and we know that it's going from -1 to 1. We need to find the width of a rectangle. So if we're going to make these rectangles, how many rectangles are there? We're going to have n rectangles, and the width is going to be 1 minus, we go right minus left, divided by n. So we have 2 over n is the width of a rectangle. All right, now let's look at x values. So if we have the graph, we're starting at -1. The first rectangle, the x value of the first rectangle is going to be -1 plus 2 over n. The next x value is going to be -1 plus 2 times 2 over n. And then as we move over, we have the ith rectangle, which is -1 plus I times 2 over n. And once we get to that point, after making a table and thinking about it a couple of times, that's all we really need. But let's go ahead and make the table to make sure we know what's happening with the x values and the y values. If we have y values, we can find area. So the first x value is that. The next x value is that. So we're just looking at the first x value. And here we'd be using right-hand rectangles. But it won't matter if we use left or right rectangles because we're going to use infinite rectangles. Okay, so that continues on until we have the ith rectangle. And then that continues on until we have n rectangles. So we can check to make sure that's the right endpoint. If we cancel the n, it's -1 plus 2 is 1, and that means we would be at the right endpoint of the interval. All right, then we have to find y values. So that's going to be 1 minus x squared, and x is that. 1 minus x squared, and x is that. Okay, we can continue. Here's the one that we really need, 1 minus x squared, because we don't want to write every actual representation of y values. We want to find a generalization of the y value, which means the ith y value, and then we can find area. Okay, so let's find the area of the ith rectangle. So area is going to be height times base times height. Okay, let's do area of n rectangles. The area of n rectangle is going to be the height times the base. So that's the area of one rectangle, and then when we add them all up, this is the area of n rectangles. And from here it's just algebra and then find a limit. Alright, so we have to apply that, simplify, and then find the limit. So if we square that, we don't just square this and square that. We have to go use FOIL. We have to distribute all that. But we're squaring the whole thing. So let's simplify this part. 1 minus negative 1. No. This whole thing is squared here. We have to square that. Then we'll apply the 1. And then multiply by 2 over n. So let's copy the 1. And then we're going to have 1. This times this, and then this times this, so we're going to get negative 2i, 2 over n. Alright, and then we're going to square this, and we have I squared, 4 over n squared. Okay, and then that's times 2 over n. Okay, we have, that'll be a 4 over n. Let's write it one more time, and we can also take care of that. 1 minus 1 is gone, and then we're going to go minus a negative, so that's going to be positive 4i over n. 2 times 2i over n, negative times negative is a positive. And we're going to go negative 4i squared over n squared, and that's times 2 over n. Alright, distribute that, and that'll be 8i over n squared. So we're distributing n and 2. Here we're going to get 8i squared over n cubed. Alright. So now since we want to focus on this I and that I squared with the sigma, let's have two summations, and we can put the 8 over n squared in front. I equals 1 to n of I. So that 8 over n squared can go in front because this only affects the I. Then we're going to have 8 over n cubed summation of I squared, and we have formulas for summation of I squared and summation of I. So now we just substitute the formula for that. Summation of I squared is n plus 1 over 2, and summation of I squared is n plus 1, 2n plus 1 over 6. We've already calculated that before, so I'm just going to write down the polynomial of that. We can expand that. 8 over n squared. And that'll be n squared plus n over 2. And here we have 2n cubed plus 3n squared plus n over 6. All right, and then we're just going to rearrange that. 8 over 2, we can make that a 4. And then n squared over n squared and n over n squared. So we put the n squared under each of those and put the 2 under the 8. And then we have 8 over 6, so that's 4 over 3. And then 2n cubed over n cubed. 3n squared over n cubed. N over n cubed. All right, and this is the area of n rectangles, and we need to find the area of infinite rectangles. So that'll be a 2 plus 3 over n plus 1 over n squared. And then we just find the limit as n goes to infinity. Let n go to infinity, and that'll be the area of infinite rectangles. All right, so as n goes to infinity, that's 0, 0, 0. And we have 4 times 1 minus 4 thirds times 2. 4 minus 8 thirds. And that will be 4 thirds. So the exact area under the graph is 4 thirds. No more approximations because we used infinite rectangles. So the area under the curve is 4 thirds. All right, I had one more example, but we've gone so long, I think we'll stop.